Good afternoon, friends. I'm Dr. Balakrishnan, working as Associate Professor in the Department of Mechanical Engineering. Today's our topic is the composite materials, in particularly the introduction. This subject is really important to understand the fundamentals of composite materials and to its various strength and mechanical behaviors. And you can be in a position to design the composite laminates, and strength analysis will be the course objective. And course outcomes related to this subject is you can be in a position to explain the properties of fibers and reinforcement. So with this course outcome, we are going to discussing about the various learning objectives to understand what is a composite material and to understand why composite is superior than monolithic alloys. And the learning outcomes of this session, at the end of this session chapter, you will be in a position to infer what is a composite material, and you can be in a position to illustrate the different types of composites, and you can also enlist the various applications of composites. Normally you can come across many various metals which is related to the metals, polymers, ceramics and composites are the common four basic categories of structural material. In this, metals are dominating materials for the past centuries because of many advantages, and the common materials are the aluminum, copper, magnesium, zinc, lead and nickel and titanium are the common metals. And the structural applications, alloys are more frequently used than pure metals because of its various advantages like high strength and corrosion resistance, wear resistance, and good toughness property can be achieved when it is being added with some specific alloying element. Because of these reasons, the alloys are used. And the name itself, alloys are formed by mixing a different material. Sometimes it can be included with non-metallic materials too. And alloys offer better properties than pure metals. For example, cast iron is brittle and it is easy to corrode, but the addition of less than 1% of carbon in iron makes it very tougher, and the addition of chromium makes it very corrosion resistive. Though the principle of alloying thousands of metals or alloys are created because of the chance of adding many alloying elements with the metals. And metals are in general heavy as compared to the plastic and composites. Only aluminum and magnesium, beryllium provides densities which is closer to plastics. But steel is 4 to 7 times heavier than plastic materials, and aluminum is 1.2 to 2 times heavier than plastics. So normally steel, you may know, it is 7.8 grams per cc, while it is aluminum is 2.4 grams per cc. So you can have a clear comparison between the aluminum and steel. And metals generally require several machining operations to obtain the final products. And metals have high stiffness, strength, thermal stability, and thermal and electrical conductivity. Due to their high temperature resistance than plastic, they can be used for applications with higher service temperature requirements. In plastics, in the past 5 years, the production of plastics on volume basis has exceeded the steel production. Yes, friends, it is very known fact is iron is the highest potential we have in our universal earth crust. That is the reason why the steel is playing a vital role, and alloys of iron is playing a vital role of low production cost and easy availability and various attractive properties. And plastics is being picked up for the past 5 to 10 years of period due to their lightweight, easy processability and corrosion resistant, and plastics are widely used for automobile parts, aerospace components and consumer goods. And plastics can be purchased in the forms of sheet, rod, bar, powders, pellets and granules. With the help of manufacturing process, plastics can be formed into near net shape or net shape parts. They can provide high surface finish and therefore eliminate several machining operations. This feature provides the production of low cost part. Plastics are not used for high temperature applications because of their poor thermal stability. Yes, it is very weak. In general, the operating temperature for plastics is less than 100 degrees Celsius is another disadvantage. And some plastics can take service temperatures in the range of 100 to 200 degrees Celsius without significant decreases in the performance. And plastics have lower melting temperatures than metals, and therefore they are easy to process. And the third metal category is the ceramics have strong covalent bond and therefore it provide great thermal stability and high hardness. They are most rigid of all the materials which we have been discussed in steel or plastic. And the major distinguishing characteristic of ceramics as compared to metals is that they possess almost no ductility. Because of its high hardness offering capacity, it possesses zero ductility or minimum ductility, and they can fail in brittle fashion. Because of poor ductility, it will fail in brittle mode. And ceramics have highest melting points of engineering materials. For example, if you talk about the aluminum oxide, Al2O3, the other name it is called alumina, it will have minimum 2600 degrees Celsius of melting temperature. And they are generally used for high temperature applications, and naturally it offers high wear resistance, so it can be a candidate material for wear resistance applications and most form of chemical attack. And ceramics cannot be produced by common metallurgical technique, and it requires a high temperature equipment for fabrication. And due to their high hardness, ceramics are difficult to machine and therefore require it to be a net shaped forming or final shape production. And ceramics require expensive cutting tools such as carbide or diamond tools. And the fourth category of material is the composites, because composites material have been utilized to solve technological problems for a long time. But only in the 1960s did these materials start capturing the attention in industries with the introduction of polymeric based composites. Since then, the composite materials have become common engineering materials and are designed and manufactured for various applications including automotive components, sporting goods, aerospace parts, consumer goods, and in the marine and oil industries. The growth in composite usage also came about because of its increased awareness regarding product performance and increased competition in the global market for lightweight components. Among all the materials, composite materials have the potential to replace widely used steel and aluminium, and many times with better performance. Replacing steel components with composite components can have save 60 to 80% of the component weight and 20 to 50% of the weight by replacing aluminium part. Today it appears that composite are the materials for choice of many engineering applications. As we discussed in the previous slides, we come to understand that the density of the steel is around 7.8 grams per cc, while the density of the composite can be started with, if you talk about the aluminum composite, then you can be comparable with 2.4 grams per cc of aluminum, and it can be getting increased by the addition of the fraction of addition of the reinforcements. So the composite material is not a new or recent one, because nature is full of examples with composites. For example, if you see the coconut palm leaf, for example, it is essentially a cantilever beam like, and it is added with some fibrous composite, because cellulose fiber in a lignin matrix. The cellulose fiber have high tensile strength, but they are very flexible, that is low stiffness, while the lignin matrix joins the fibers and furnishes for the stiffness. So the combination of property can be obtainable by using the combined effect of the cellulose and lignin matrix. And bone is another example of a natural composite that supports the weight of various members of the body. It consists of short and soft collagen fibers embedded in a mineral matrix called apatite. Nevertheless, one can safely mark the origin of distinct discipline of the composite material as the beginning of 1960s. As one should understand, since we discussed in the previous slide, the composite is not a new one, and it may be from the evolution of the earth, yes, but the application of composite materials to the engineering industry is start picking up from 1960s. That is the reason why it is being claimed as the composite science, and its application is starting from 1960s. And it would not be too much of mark to say that a concerned research and development effort in composite materials began in 1965. Since the early 1960s, there has been an increasing demand for materials that are stiffer and stronger, yet lighter in field as diverse as aerospace, energy and civil construction. And as you know, the materials perspective, we have more than 50,000 engineering materials. Maybe something may not find a real application still, but if you take consideration about the list of engineering materials, it can cross more than 50,000. But the choice of the materials for engineering applications is depending upon many factors, starting from density and tensile modulus, tensile strength, specific modulus, specific strength and maximum service temperature. Each and everything is contributing, is the deciding factor to choose a specific material for a specific applications. So from this table, one can able to understand some of the physical and the mechanical properties of the material. Starting from metals, it can have cast iron grade 20 and SAE steel of 1045 and aluminum of 2024 with T6 T4 condition. It depends upon again the material to material. So if you look for high density, then it will be about steel is highest one. In this table, steel is highest one. It is 7.8 grams per cc. While if you look for low density metal, then you should go with the polypropylene. If you look for low weight, then you should go with light density material. If you look for high strength, you should go with the tensile strength. In this table, the highest strength available here is carbon epoxy fiber 1.73 gigapascal. So one can have a different prospects to decide which I am looking for. If you look for specific modulus, then you should go with the highest. If you look, then the Kevlar epoxy, and lowest if you look, then you should go for 1.55, that is polypropylene. And specific strength, if you look for high specific strength material, then you should go with carbon epoxy, that is 1.08. And if you look for maximum service temperature, then you should pick the material which is alumina, that is working about 1425 degrees Celsius to 1540 degrees Celsius, that is operating temperature, servicing temperature. So it is really a tough task to decide which material is suitable for my application. You should think about the real necessary properties of the component. Accordingly, you can select a material. That is the challenge for a design engineer. And now, what is composite? So since then we have been discussed the various materials categories, starting from metal, plastics, ceramics and composite. Then what is a composite in specific? It consists of two or more physically distinct phases, that is matrix and reinforcement, with an interface spacing between them. And composites are made up of two phases, the matrix and reinforcement phase, and there will be a separating phase is called interface. And composites are one of the most widely used materials because of their adaptability to different situations and the relative ease of combination with other materials to serve specific purposes and exhibit desired properties or desirable properties. The main advantage of composite materials are their high strength and stiffness, and combined with low density when compared with bulk materials. So in this juncture, we should think about the density and higher strength, specific strength. So the thickness to strength ratio and thickness to weight ratio, it plays a vital role when we choose a material for high mobility. So for example, automobile applications, it looks a high strength with light weight. So in this case, definitely composite material will be a suitable solution for giving a perfect combination of both high strength and light weight. So for example, if you look for high strength for a case of about 750 megapascal, then you should go with steel and its alloys only. So another material can solve this problem. Then if you look at steel, then you should think about the density. It crosses about 7.8 grams per cc. But the same strength can be easily achievable by the application of composite materials like aluminum alloy composite, when it is added with the silicon carbide particles. It can give 650 megapascal or 700 megapascal strength for pure aluminum alloy even. So this gives 1/3 of the density, 1/3 of the weight. I can go with the high strength. So that is the beauty of selecting a composite materials. To enhance the materials property, the performance efficiency is the primary reason why we people are really adapting or really inclined towards composite manufacturing. And it can have a chance to design materials with combination of desired properties. And phases of composite, the matrix phase is a continuous phase and which surrounds the reinforcement phase. From this diagram we can able to understand that continuous and discontinuous phase is a reinforcement and continuous phase is a matrix phase. And the composites are engineered materials made from 2 or more constituent materials of at least 5% with significant different physical or chemical properties. Yes, it is very important point to understand here is the 2 phases what we discussed are the reinforcement and matrix phase. Both of these materials will have a different physical and chemical properties and which remain separate and distinct with the furnished structure. In this juncture we should also think about the alloy. Actually the alloys are made with 2 or more different constituent element. And similarly the composite are also made with 2 or different elements. Then what is the difference between composite and alloy? Alloy will be made as a homogeneous mixture, that is the alloys will be available in solid solutions or other way in precipitates, but composites are separate when it is being even made with the composite. For example, reinforcement phase will be reinforcement phase and the matrix phase will be a matrix phase. You can easily distinguish which is a matrix and which is a reinforcement in after manufacturing of composite. Even through NACDI also you can able to see. For example, in bamboo leaf or the bone which we talked about a little earlier, and the banana leaf or something other composite materials, you can able to distinguish what is a reinforcement and what is a matrix. But in alloys it is not possible to distinguish in an NACDI or under microscope, even not possible to identify which is a solvent atom and which is a solute atom. So what is an alloying element? It is not possible to distinguish after making of alloy. So that is the difference between alloy and composite. So in composite remain separate and distinct with the furnished structure. That remain means the reinforcement phase and matrix phase are remain separate, but in alloys it does not remain separate, it is mixed as a solid solution or precipitate. Why composite are important? Because the composite can be very strong and very stiff and it very light in weight. So ratios in strength to weight ratio is possible and stiffness to weight ratio are easily achievable greater than steel or aluminum. The same stiffness can be achievable with lightweight. That is the beauty of composite. And in addition to the points which we discussed in the earlier slides, fatigue properties are generally better than common engineering metals is the another advantage of composite, and toughness is often greater too. And composite can be designated that do not corrode like steel. Yes, if you want to make a steel as a non-corrosion material, then you should add costly materials called chromium, costly elements, costly alloying elements like chromium or nickel should be added to make the steel as non-corrosive, make the steel as stainless. But in composite it can be easily achievable without making much of the alloying elements, and it is possible to achieve combination of properties which cannot be achievable in metals, ceramics or polymers alone. When it is being alone, it is not possible to achieve this kind of combination of properties. But when it is added with the matrix, the formation of a composite material, then it is possible to achieve a combination of properties. But you cannot claim all the time it has a advantage and huge potential for large applications. It is not like that. But even composites also have some disadvantages. That is, properties of many important composites are anisotropic. It is a point to seriously thinking about. It offers a different property with respect to different loading directions. It has to be think very well when you choose a composite material for your application. And it is generally expensive. Composite materials are generally expensive, may in the way of matrix selection or the reinforcement selection. And again, the third important disadvantage of composite material is manufacturing methods for shaping of composite materials are often slow, and it is costly. And coming to the constituent of composite material, as we discussed in the previous slides, matrix phase is a continuous phase, and it is the primary phase, and the dispersed or reinforcement phase, and it is called a secondary phase, and it is embedded in the matrix in a continuous or discontinuous form. And the third one is interface. It is the zone across which the matrix and reinforcement phase interact with chemically, physically, and mechanically. So functions of the matrix material, primary phase or continuous phase: it protects the environment, it protects the reinforcement phase from the environment, and it transfers the stresses to the reinforcement phase, and it holds the embedded reinforcement phase in place, usually enclosing and often concealing it. When a load is applied, the matrix shares the load with the secondary reinforcement phase. In some cases, it deforms so that the stress is essentially borne by reinforcement agent. And functions of the secondary phase, that is reinforcement, the secondary phase are embedded in the matrix in the primary phase, may be continuous or discontinuous. It depends upon the type of reinforcement which we select. And dispersed phase is usually stronger than the matrix, therefore it remains called reinforcement phase. And the reinforcement imparts special physical and mechanical electrical properties to enhance the matrix properties, and materials properties a combination of these two. So as we discussed, the primary phase is the matrix phase. Matrix phase is normally lesser strength than your reinforcement phase. Yes. And reinforcement phase is again stronger than the matrix phase. Then what will be the property of the composite material? Then the material property of the composite is the combination of these two will be achievable. And we can define an interface between the reinforcement and the matrix as a bounding surface between the two, which across the discontinuity some parameters occurs. Yes, we have a matrix and we have a reinforcement. In between there is a phase called interface, and thus that discontinuity across the interface may be sharp or gradual. Mathematically, interface is a bidimensional region because it has both length and breadth, but thickness can be eliminated because of very less in dimension. In practice, we have interfacial region with finite thickness. The thickness also to be considered. In any event, an interface is the region through which material parameters such as concentration of an element, crystal structure, atomic registry, elastic modulus, density, coefficient of thermal expansion, etc. can change from one side to other. So clearly, a given interface may involve one or more of these items. The behavior of composite material is a result of the combination behavior of following three entities, that are fiber or the reinforcement element, matrix or fiber matrix interface. So because of these three elements only decides the final property of the composite material. And the advantages, yes, naturally it offers a less weight, high stiffness, high strength, improved corrosion resistance, customized for application use in lightweight structures are the key benefits of composite material. And today's applications: boat hulls, sport equipment, rackets, skis, automotive components, many automotive components. I cannot able to enlist here everything here, because starting from automobile bodies and moving to the engine components like pistons and gudgeon pins and crankcase, everything is nowadays is keeping changed with the existing materials like cast iron and other aluminum by the various combination of composite materials. And it picks a very good applications in biomedical products, artificial limbs, artificial implants, and tissue engineering, composite materials, tissue engineering, And underground pipes, nowadays all the pipes are not made with cemented pipes. It is being easy to transport by if it is made with the composite materials pipe. And aircraft, aerospace structures, marine components, and various automobile parts are now applied with the composite materials. And for the sake of convenience, I am presenting here the locations and the parts which are available as composite material in commercial aircraft structures, starting from the cargo floor panel, which is being located here. The cargo floor panel is made with fiberglass epoxy aluminum composite material, and here air conditioning duct is made with carbon fiber BMI composite material, and here the S duct is also made with carbon fiber and epoxy resin, and here the VAR antenna, it is also made with fiberglass epoxy. You see here 1, 2, 3, 4, 5, 6, 7, 8 different locations are being highlighted here in this commercial aircraft structure. And military aircraft components, you see here leading edge radome and canopy arc, and then canopy fairings and forward fuselage and ejection seat and high band radome and main landing gears and whisking panel, main engine fuel pump. Everything is made with composite structure nowadays. And engine components, you cannot omit some of the composite materials applications even in high temperature locations too. You see inlet guide vane and exhaust flap, where is normally the gas is being emitted here, exhaust flap which is made with carbon fiber and PMR 15 composite, and electronic housing which is also made with carbon fiber and BMI, and main engine fuel pump which is also made with carbon fiber and BMI. You see the high temperature applications even nowadays is replaced by existing materials by the application of various composite structures. And you can also claim some of the applications which related to the satellite components, carbon fiber tubing and shear panels and brackets fittings and integrally stiffened bus panel and feed horn antenna, everything, many locations, 3 plus 3, 6 different locations is being highlighted in this picture. And in automotive industry, the composite materials have been considered the material of choice in some applications of the automobile industry by delivering high quality surface finish and styling details and processing options. And manufacturers are able to meet automotive requirements of cost, appearance and performance utilizing composites. Today, composite body panels have successful track record in all categories, from exotic sports cars to the passenger cars to small, medium and heavy truck applications. In 2000, the automotive industry used 318 million pounds of composite materials. And because of automotive market very cost sensitive, carbon fiber composites are not yet accepted due to their high material cost, but automotive composite utilize glass fibers as main reinforcement. And average use of composite in automobiles per year since 1988 and 1993, bumper beam, sheet, load floor, hood, radiator support and roof panel and other areas. And barriers in composite markets, actually yes, it has many advantages and disadvantages. Then what is still making some barrier? One design engineer cannot choose a composite material as a candidate material for his specific design. The primary barrier of the usage of composite material is their higher initial cost in some cases as compared to the traditional materials. And regardless of how effective the material will be, its life cycle, industry considers high upfront cost. Yes, the composite material is also like a fluctuating market. Because of that reason, the production of the composite material also may be ups and down. And in general, cost processing of composite is high, especially in hand layup process. Here raw material cost represent a small fraction of total cost of the finished product. And there is already an evidence for work moving to Asia, Mexico and Korea for these cases where labor costs are significant portion of the total product cost. So it is also making, again, because of the maneuverability with manufacturing of composite, the manpower and the manpower cost should also be considered when we choose a composite material as a candidate material for my automobile applications. And the biggest challenge of the composite material is the recycling of composite material is the biggest challenge when penetrating high volume markets such as automotive industry, where volume production is in millions of parts per year. With the new government regulations and governmental awareness, the use of composite has become concern and poses a big challenge for recycling. It is a different chapter to discuss. So summary, basic categories of structural materials we have been discussed, and what is a composite material, it is also been discussed, and why composite are important, also been discussed, and constituent composite materials like the matrix material, reinforcement material, and interfaces, and functions of the matrix material, it carries the reinforcement, and functions of the reinforcement material, it carries the load from it takes the load from the matrix material, and it can be taking higher load when compared to the matrix material. And today's application, we start from the automobile applications and the road transport, rail transport, and also the aerospace applications and biomedical applications were being discussed. And then questions for thinking and discussing. What is the difference between composite material and the monolithic metals and alloys? Yes, we have been discussed. My friends, you please rethink about the lecture material and discuss yourself and come with your solutions. And what is meant by specific weight and how it is advantageous in vehicle mobility, because it is an important property which is being claimed many times is the chief advantage of composite materials. So we should understand what is meant by specific weight and how it is being advantageous with vehicle mobility, and what is meant by specific strength, how it is advantageous in vehicle mobility. So with these three questions, may I wind up this session. Thanks for your patient listening. Please discuss with yourself and come with a fruitful discussion. Thank you very much.